Good morning, doctor, and welcome to my presentation on assignment 1. So in this presentation, I'm going to go through my report and explain my approach. I also put up my code here for a better visualization, also to track my workflow. Okay, so let's start it. So in this assignment, we were required to train a machine learning model to predict target life expectancies of different countries by using the provided features in the dataset. So first of all, I loaded the data into Jupyter Notebook using Pandas. It included multiple features such as demographic, health, and economic indicators that potentially influence the life expectancies. And then I performed some EDA, which stands for exploratory data analysis, to understand the data set structure and identify the potential issues that could impact the model performance. And here are the key steps. So first of all, I have to filter out all of the unnecessary features from the dataset that which are irrelevant or redundant. So these features were detected by using confusion matrix shown in figure 1.1. So here's the confusion matrix that I have generated. And then I created a copy of the training dataset to remove all the unnecessary features. So based on this confusion matrix, ID, country, business, and population were removed because they have a very low correlations with their target. Next up, I checked for the missing values and duplicated values, and the data sets were examined for missing value and duplicated values. And the results showed me that the amount of missing values were too small compared to the whole size of the whole data for each features. So I decided to remove all of the missing values and duplicated values to ensure we have a clean data set for model training, and this did not impact much on the training data size. Next up, I use histograms to detect outliers for the dataset, and then I use interpolator range method to detect the extreme values. Here's the graph of histogram, and any data points that were 1.5 times the interpolator range or less were identified as outliers. And then I apply log transformation to skew the columns with extreme outliers. Lastly, I use clipping to cap extreme values within acceptable ranges, preventing them from distorting the model's learning process. And here's the graph showing the data after handling outliers. The data is normally distributed. After the data is clean, I move on to model training process. So I divided the data into training set and testing set, 80% for training set and 20 for testing set, using train test split from sklearn library. So since this was a regression problem as the outputs were continuous values, I chose 4 regressions model to train using sklearn, which were linear regression, decision tree regressor, random forest regressor, and extreme gradient boosting regressor. Next up, I use cross-validation to perform k-fold with 5 splits to ensure a stable performance estimation and avoid consuming too much of validating time. For hyperparameter tuning, I use research cross-validation to find the best combination uh, to work for a particular model. It uses cross-validation to assess each combination after doing an exhaustive search across a predetermined set of hyperparameters. These two were to optimize decision tree, random forest, and extreme gradient boosting regressor as they have hyperparameters. I didn't use hyperparameter tuning for linear regression because that model didn't have a hyperparameter. Next up for model evaluation. So I used 3 evaluation metrics for regression, which were mean square error, mean absolute error, and R-squared score. And for the result, according to figure 3.1, which is down here, the linear regression performed the worst among the models. It had the highest MSE and MAE score with the lowest R-square of both cross-validation score and actual predicting score. So this suggests that it has a very poor fit. For next model is the decision tree regression, show a better performance than linear regression, but was prone to overfitting. Why its MSE, MAE improved is R2 R-square score of indicated that it still lacked a generalization ability. Next up for random forest. So this model provided a lower MSE/MAE than linear regression and decision tree regressor, indicating that lower prediction errors, and it achieved higher R-square score, explaining more variance in life expectancies than other two models. And it showed a strong consistency between cross-validation score and actual test performance. This indicates that the model not only fits the training data well, but also maintains accuracy on unseen data. So, seen random forest regressor is like a improved version of decision tree regressor. It overcomes overfitting issues by averaging multiple trees, making it more reliable and reducing variance. Lastly, for extreme gradient boosting regressor model, it delivered the lowest MSE and MAE, indicating that the most accurate predictions with minimal error, and it also achieved the highest R-square score, meaning that is explained in the largest proportion of variance in the life expectancies among all other models. And it also showed a strong consistency between cross-validation score and actual test, indicating that it overcome the overfitting problem. Next up for graph analysis between the actual and predicted life expectancies for each model. So first of all, for linear regression, as you can see here from the graph, the points exhibit a general trend along the diagonal, but with a significant spread between each point. And predictions showed a high variance, meaning many values deviate far from actual values. So this suggests that the linear regression struggles to capture the complex and nonlinear relationships in the data, leading to high bias, meaning that the data is being underfitted. Next up, for graph for decision tree regressor, the prediction have improved compared to the linear regression, but discrete cluster points indicating overfitting and decision tree tend to fit the training data too precisely and may result in poor generalization to unseen data. So predictions are inconsistent, with some actual values being having significant different predicted values. And for random tree regressor, the points are now mostly aligned along the diagonal, indicating a strong predictive performance, and the threat is minimized. And there are fewer extreme deviation, meaning this model has better balance between the capturing patterns and generalizing well. And the assembled nature of random forest mitigates the overfitting issue seen in decision tree, providing a more stable and reliable prediction. And lastly, for the uh, extreme gradient boosting regressor, the data points are tightly clustered around the diagonal. It achieved the highest predictive accuracy among all models, and this also a minimal spread of points, showing that this model balances complexity and generalization, capturing non-linear relationship without overfitting. Okay, and for model selection and prediction, um, we all can see that extreme gradient boosting regressor was chosen as the final model not only because it produced the best evaluation scores, but also because it exhibited the most stable and consistent performance. And additionally, its gradient boosting mechanism builds upon the strength of decision tree while minimizing overfitting and bias through iterative improvement, leading to superior predictive accuracy. So that's why I chose this one. It was the best model for final prediction of life expectancy on the test set. And for conclusion, while linear regression was too simplistic to capture complex relationship, and decision tree regressors showed signs of overfitting, and HGB regressor out, outperformed all other models in terms of accuracy, consistency, and it achieved the lowest error rates and highest R-square score, demonstrating its strong ability to explain variance in the data and generalize well across different samples. And for future work to improve my training model skill, I could use some neural networks, which are deep learning models and can capture nonlinear relationship in huge or higher dimension data sets. And I could use feature selection methods to eliminate less important characteristic and simplify the models such as lasso regulation or recursive feature elimination. And lastly, I could explore more external data sets that offer additional health, demographic, or socio-economic indicators to enrich the input data and provide a broader context. And here are all the graphs I've included inside the appendix. Thank you for listening. This is the end of my presentation. Thank you.